productive good day to all. One more lecture on the series of mathematics, series of lectures in the subject mathematics 2 for the JNTU Kakinada R20 regulation. And that unit 1, we completed so far 5 topics, 5 lectures, series of 5 lectures. In that one, till normal form we completed, and a little extension of the normal form is the parallelly finding the normal form of the given matrix. At the same time, we can extract two non-singular matrices from the given matrix. That process we are going to check it now. Yeah, please follow this. Here, the given matrix can be rewritten here. A equals to I, A, I. And that's nothing wrong in that. Means I'm multiplying a matrix with an multiplicative identity, so which doesn't make any difference. In this one, here the bigger question is, in between there is a product. Product means matrix multiplication is supposed to exist. For that one, we need to check the conditions too. For example, if A is of order m by n, then first matrix, this is known as a prefactor. This is known as a prefactor. And its order is supposed to be m by m. And A as same as this m by n. I, this is called a post factor. Post factor, which is of order n by n. So m same. At the end, I may get m by n. N will be same. So I may get m by n like that. In this one, what I am trying to do is by using the operations, by using elementary row operations, it's supposed to convert into normal form. In the process of normal form, whenever I'm using the row operations will be applied on this prefactor. Row operations will be applied on this prefactor. Whenever the column operations are applied on that, column operations will be applied on post factor. That's the post factor. That's what. So that's let us see an example, then we may come to know that. So this, the question might be asked like this: find the two non-singular matrices P and Q such that PAQ is normal form, where A is 1, 2, 3, 2, 1, 2, 3, minus 2, 2, minus 2, 1, 3, 3, 0, 4, 1. So clearly it is consists of 3 rows and 4 columns, 3 by 4. Then the order of the prefactor would be the 3, order of the post factor would be 4. In this, when first I am trying to reduce elements below A11 to 0. For that reason, I need to check this to 0, I need to check this to 0. For that, I need to multiply row 1 with 2 and subtract row 1 with 3 and subtract here. Then I may get this. So here I use the only row operation, means the row operations will be applied only on the prefactor. So in that R2, R3 disturbed. So R1 is not at all disturbed. So R1 will be as it is. R2 is 2, R2 minus 2 R1. So 0 minus 2 minus 2. R2 minus 2 R1. So 1 minus 0 is 1. 0 minus 0, 0. Similarly, R3 minus 3 R1. R3 minus 3 R1. 0 minus 3 minus 3. 0 minus 0, 0. 1 minus 0, 1. That's what here. Similarly, so row operations completed. Then I am coming to the column operations. 2, 3, minus 2 is opposed to 0 with help of this one. So here C2 prime is C2 minus 2 C1, C3 prime C3 minus 3 C2, C4 prime C4 plus 2 C1 1. That's what with respect to 1 only. Then whenever the column operations are applied, that will be affected only this. So C2 minus 2 C1. 0 minus 2 minus 2 means C1 is not disturbed, so C1 as it is. C2 will be C2 minus 2 C1. C3 will be C3 minus 3 C1. C4 will be C4 plus 2 C1. That's what the process here. Now the elements below and beside are 0. Now I need to jump from here to here. A22. Again, below A22 there is one element, so one operation is supposed to hold R3 primes, R3 minus R2. Then beside two elements we have, so two elements. Now we got this way. For the convenience, what we tried is divided this with 6. But I don't want to encourage you to do that, because if I divide it here, we may get a fractional value, sir. That makes a little tough task. So that's the reason I don't want to entertain that. You please check with the same. Means here, what I may write here, it is C3 primes interchange, because the both are relatively prime. 6C3 minus 5C2. So interchange that one. C4 primes 7C2 6C4 plus 7C2. If you do that one, no doubt these two will be 0. It will be minus 6. It will be minus 6. These two will be zeros. And here, this fractional values can be avoided. Of course, that's up to your choice. That is up to you. And this one, we can do this one also. Even we can do this one also. Options yours. And finally, it is converted to I200. Then this one pre-factor is taken as a P, post-factor is taken as a Q. So these two are non-singular. How can you say that they are non-singular? Simply, if you find the determinant of the matrix, the determinant should not be 0. Let us check here whether it is 0 or non-zero. Shift 4. I'm going to define a matrix. First dimension, matrix B, because matrix A I have earlier, 3 by 3. Then the data is 1, 0, 0, minus 2, 1, 0, minus 1, minus 1, 1. So this one. Now its determinant I supposed to check. Shift 4. I want the determinant 7 of matrix B. Again shift 4. Matrix B is 4th option. Close it. I got 1. Means which is non-zero. That's what. Similarly, you may try another set of problems here. Yeah. So similarly, you may try this set of problems also. PAQ equal to normal form. Now, we will use actually to find the inverse of the matrix. What we usually try earlier is A into adjoint A equal to determinant of A times I will write. Then pre-multiplying with A inverse. A inverse times A into adjoint A equals to A inverse times determinant of A into I, and from here A inverse equals to, I may write here, or let me write on one more step, A inverse times A adjoint A equals to A inverse times this determinant of A. A inverse times A will be I, multiplied identity. So I may get here A inverse equals to 1 upon determinant of A times adjoint A. This actually will try. But this method is advisable up to 3 by 3. Up to 3 by 3. Because what's the major issues in that one is adjoint of A means I need to find the transposition of the cofactor matrix. Cofactor matrix I need to compute, and then I need to transpose this one. Up to 3 by 3 means for 9 elements you need to compute the what do you call this cofactor. And but if it is a 4 by 4, then hectic to it will be tough task to compute the determinant as well as the cofactors. So that's reason to overcome this one, we can do the same by using the Gauss-Jordan's method. Whenever the Gauss method is there, we need to use only elementary row operations. We'll use only elementary row operations. So let us check that one. How to check this? The matrix A is, I think I can write like this: I equals to A equal to IAI. But in PAQ equal to normal form, we studied that this I is known as a prefactor, and we'll use only row operations. So that's the reason wantedly I wrote A equal to IA. Now, if a product of these two matrices is I, means whenever this will become I, then this will become another matrix B into A. Means product of the two matrices will become I, means this B is known as inverse of A. This B is known as inverse of A. So this method is pretty comfortable, whatever the bigger order it might be. So whatever the bigger order. So in Gauss method, Gauss-Jordan's method, we will use only elementary row operations. So if I go with an example here. Now if I see this problem, let it be the matrix A. Let it be the matrix A. This one I'm going to write here: A equals to I A. So 1 1 3 1 3 minus 3 minus 2 minus 4 minus 4, which equals to, since it is a 3 by 3 matrix, I can write here 1 0 0 0 1 0 0 0 1 into A. This is quite similar to the normal form equal to PAQ. In that one, post factor I'm not using, because in the post factor we usually apply only column operations. So here I'm not using any column operation. That's the reason I discarded the post factor. Now in this here, by using this, I supposed to reduce to this 0, means I need to convert row 2 primes, row 2 based on row 1, and R3 also I need to reduce R3 based on R2. Now here I'm checking this balance 1 1, so directly subtraction. Here 1 minus 2, so if I multiply R1 with 2 and then add R1 with 2 and then add, so I may get here 1 1 3 0 0 wanted, forcefully we made this to 0. Then here R2 minus R1 means 3 minus 1 will be 2, minus 3 will be minus 6. and R3 plus 2 R2. So minus 4 plus 2. Minus 4 plus 2 will be minus 2. Here minus 8 plus 6 will be minus 2 equals to the same operations to be applied on the prefactor. So in this prefactor, R1 is not altered, 1 0 0. R2 is R2 minus R1, 0 minus 1 minus 1, 1 minus 0 1, 0 minus 0 0. R3 primes R3 plus 2 R2, R3 0 plus 2 2, 0 plus 0 0, 1 plus 0 1 times A, and further, oh sorry, due to some technical issues here it is not erasing. Anyhow, this is A, this is A. Now my control will jump from here to here. By using this, elements above and below should be 0, because finally I need to get an identity matrix, means only principal diagonal element must be 0, only above below the principal, other than the diagonal elements should be, principal diagonal element should be 0. So I need to change here R2, sorry, R1 primes R1 based on R2, and R3 also I need to update R3 based on R2. So what I may get here? Here 2, here is 1. If I multiply R1 with 2 and then subtract again, if I multiply R3 with R3 with 1, directly subtraction is sufficient. So in this one, R2 is not altered. So 0, 2, minus 6. Earlier we made this to 0, now we made these two are 0. Like that only we adjusted our operations. Now this position is R2 prime, R1 primes 2 R1 minus R2. So 1 minus 0, 2 times 2 minus 0 is 2. Here 2 R1 means 6. Here minus of minus plus 6. 6 plus 6 will be 12. And here R3 minus R2. 0 minus R3, sorry, it's plus because both are different signs. It's supposed to be plus. So 0 plus 0 0, minus 2 plus 2 0, minus 2 minus 6 will be minus 8. Equals to the same I need to apply here. Second row will be as this, minus 1 1 0. First row will be R3 2 R1 minus R2. 2 R1 will be 2, 2 minus of minus plus, 2 plus 1 3, and 0 minus 1 minus 1, and 0 minus 0 0. Here R3 plus R2, minus 2 minus 1 plus 2 will be 1, 1 plus 0 is 1, 1 plus 0 is 1. Yay. Now my control will jump from here to here. My control will jump from here to here. Now what I'm trying to do is here, R1 I need to update R1 with help of R3. R2 I need to update R2 with help of R3. How I need to update? Let us check this here. Here is minus 8. Here is 12. So LCM of these 8 and 12. 8 and 12, 24. So 8 and 12 is 24. So LCM would be 24, means here 12 twos, means I need to multiply this one with 2, this one with 3. Both are having this alternative signs, means need to add. Here R2 and R3. Here is 6 and 8. What was the LCM of that? 6 and 8? 18. No, it's not possible. 24 again. So 24 means here 6 fourths 24, need to multiply with 4, need to multiply with 3, and both are same sign means I need to change the sign here. So in this last 3 I haven't altered, 0 0 minus 8, and positions which we made 0, this one 0, this one 0, now these two we made 0. So with this what we may understand is number of elements to be computed are minimized. So 2 tools 4, 4 plus 0 4, first row completed, second row 4 R2, 4 R2 means 8 equals to R3 1 1 1, 2 R1 plus 3 R3, 2 R1 means 2 3s are 6, 6 plus 3 9, and minus 2 plus 3 will be 1, 0 plus 3, 0 plus 3, 3 completed. Second row here 4 R2, yeah 4 R2 is multiplying this with 4, 4 R2 is minus 4, minus 3, minus 7, and 4 minus 3, 1, 0 minus 3, minus 3, A. Now if you check properly, this became a diagonal matrix, but the principal diagonal positions are not ones. I need to check that one. R1 primes R1 by 4, R2 primes R2 by 8, R3 primes R3 by minus 8. Now if we check that, I may get here 1 0 0 0 1 0 0 0 1, which equals to your first row with 4, so 9 upon 4, 1 upon 4, 3 upon 4. Second row with 8, minus 7 upon 8, 1 upon 8, minus 3 upon 8. Third row with minus 8, minus 1 upon 8, 1 upon minus 1 upon 8, minus 1 upon 8 times A. But still, if you want to write, if you don't want to maintain this fractions inside, then do one thing: 1 by 4 and 1 by 8. Here 4 and 8 can be taken common. In that case here, 18, 2, 6, minus 7, 1, minus 3, minus 1, minus 1, minus 1 times 1 by 8 times A. This is I. So therefore, inverse of matrix B equals to 1 by 8 times 18, 2, 6, minus 7, 1, minus 3, minus 1, minus 1, minus 1. Guys, this is minus 1. So like this, we may calculate inverse of a matrix. Similarly, you may try these problems. So keep practice. Thank you.